Okay, welcome to your video lecture for section 6.5, which is on impulse functions. So in some applications, it is necessary to deal with phenomena of an impulsive nature as opposed to a sort of an off and on nature. For example, voltages or forces of large magnitude that act over a very short time period. And so these scenarios lead to a differential equation where the right-hand side, g of t, is some very spiky function in a very tiny interval, and then otherwise zero. Okay, so first here we're going to look at the integral of these forcing functions. So we'll call that I of tau, which is just the integral of g in that interval t naught minus tau to t naught plus tau. And it's a measure of the strength of the forcing function, sort of adding up the entire impulse there. And so in the case where of a mechanical system, for example, where g is a force, I of tau would be the total impulse of the force over the time interval t naught minus tau to t naught plus tau. Because g is meant to be zero outside of that interval, there is no adding or subtracting by taking the limits and letting them be negative and positive infinity, because you're just adding zero there. So in the case where t naught is zero, without loss of generality, we'll assume that for now, we often model the impulse function using this sort of step, kind of spiky step function, where if we draw this function, basically, depending upon what tau is, you have a function that's zero, and then a certain spike size, okay, and this is what obviously model that integral. And as you decrease tau, you make the spike bigger so as to keep that integral basically the same, and you can sort of continue to make these limits occur. And as you can see, as tau goes to zero, this function value goes towards infinity, but the region for which it's actually non-zero becomes tinier and tinier and tinier. And so we're going to say, okay, well, what type of function does that actually give us? You can compute the fact that this integral will always be 1 here, so it's sort of a unit impulse, no matter what we compute tau to be. Okay, so to model this idea of a strict impulse at the point 0 and nothing anywhere else, we take the limit as tau goes to 0, sort of yielding this idea of sort of this infinite mass there, but then 0 everywhere else. And this is called the unit impulse function, which is called the Dirac delta function in applied mathematics. It's really not a function because it's actually quite odd. It's a function that you essentially call the value at 0 infinite, because it has to be such that this integral is 1, even though the function is basically 0 at every single point. Okay, and so it's really what's called an idealized function or a generalized function. But we can informally talk about it as delta is equal to 0 when t is not 0, and then its integral over the entire domain is 1. So somehow we're generating area, and we're really doing it through this limiting process here, as opposed to anything sort of mathematically concrete. And of course, you can slide this thing over much in the way we've discussed about function transformation. If you want to talk about the Dirac delta function centered at t naught, you just make it 0 when t is not t naught, and then the integral would still be 1 anyway. Okay. Since we're in the Laplace transform section, we want to define the Laplace transform of the delta function, and we're going to do so through these limits of the functions with tau. So if we take the Laplace transform of the Dirac delta function centered at t naught, we really are going to take the limit as tau goes to 0 of the Laplace transform of that d tau function. Okay, since d tau is only really non-zero, in that small interval centered at t naught, the transform collapses. Okay, d of tau is just 1 over 2 times tau in that interval, and so we can bring that out because it doesn't depend upon t. Now you just have the integral of e to the minus st from t naught minus tau to t naught plus tau, which you can actually compute directly. Okay, and then doing a little bit of arithmetic in particular factoring out an e to the minus s times t naught, you're going to have basically the hyperbolic sine function divided by tau there. The initial pass of the limit is going to give you 0 over 0, but if you use one application of L'Hopital's rule, the Laplace transform of the Dirac delta function is going to be e to the minus st naught. And I like to compare this to the Laplace transform of the Heaviside function centered at t naught, which is equal to e to the minus s t naught divided by s. And so that's just something that you can compare it to. This has a little bit more to it, and you know that the Heaviside function also has a little bit more to it. You turn on the switch, it's there forever. The Dirac delta function is just sort of turning on the switch for a very, very short instance and then turning it off again. Okay, so let's solve an initial value problem with the delta function in it. So let's look at y double prime plus 3y prime plus 2y is equal to the Dirac delta function centered at 5. Let's have y be 0 initially and its derivative be a half initially. If we take the Laplace transform of both sides, collect like terms, we will have this equation for y. We solve for y and use partial fractions, so a little bit of work is done here. We'll have this expression for y. Using partial fractions gives us that expression. Since the Laplace transform of 1 over s, or the inverse Laplace transform of 1 over s is 1, we have from the previous section, since these guys are just translations of 1 over s, and e to the minus 5s is just going to take the inverse Laplace transform and shift it over 5 units, we have the solution here. Okay. And if we look at what the solution is doing here, here's the sort of initial phase, and this is due to the differential equation. Okay, so this is due to the differential equation and initial conditions, but this starts to die out quite substantially. Okay, but then at 5, we just get another prop up, and we get basically another copy of the solution over here, just a bit taller, and this is due to the Dirac delta function centered at 5, sort of giving this thing a jolt, and then the differential equations dictate the dynamics for forever and ever after that, and much like in the first phase of the dynamics, these dynamics go to 0 as well. Okay, thank you.